Okay. Because I was asking which display you wanted to record. I think you recorded that screen instead of the PowerPoint.
It doesn't matter. It's more important to have a feedback of what you're talking about. So check if you can navigate and go.
So John, should I try and stop you on questions or be nice?
You do as you see fit.
I'll be nice. Oh yeah. You got a touch over there. Second year seminar. So every Monday from 4 to 5. Second year, almost second year is Monday through Friday. Similar to this, but this is a bad.
Okay, so welcome everybody to this afternoon's Nonadiabatic seminar. And I'll start by introducing today's speaker's supervisor, Kilin, who's here, actually just lived in the office right next to me for a while now. And so he'll introduce the students and he knows much more about his background. Okay, well, thank you, Alexander, and many thanks to the Department of Physics for providing an opportunity for this talk. So it is a special talk in the sense that a great student presents at the Department of Semiconductor, which is a big one. And so to introduce the speaker, Jon Vogel joined a group in South Dakota in 2012. Since then, he published 3 papers as a first author, one as a author, total 4 as a STEAM, and around to submit a few more before his defense in 1 year. He got several talks and posters at national conferences, almost a dozen, and he got the 2 subsequent years of fellowship at Los Alamos National Lab, which means that he has either work enthusiasm or skills that they are there. And it is highly competitive summer school. So with this, I would like to invite you to get into his presentation on Photoluminescence dynamics in semiconductor materials.
All right, well, thank you, Dr. Kilin. And so, as he just mentioned, more photophysics and semiconductor materials. So if you came thinking this was thermodynamics, I'm sorry. But hopefully I'll provide a little bit of entertainment for you today. So just kind of a brief outline of what we'll take a look at. introduction and then the methods that we use in order to study these non-adiabatic dynamics, and then application into 3 different types of both nanomaterials and some bulk materials in silicon quantum dots, polyoxytitanate clusters, which are titanium dioxide quantum dots, and lead halide perovskites. And so with a couple of these projects, we've actually done some collaborative work with people here at NDSU, and I see some of their smiling faces in the audience as well. And so me being a chemist and you being a physicist, feel free to ask me questions if you would like, with my #1 goal being we're done in 45 to 50 minutes, because I'm sure everyone has something that they need to get to this afternoon. So with that, a little bit of background and motivation for why we might be interested in studying non-adiabatic dynamics, and what types of systems can this apply to. The basis for the bulk of my research has been focused on renewable energies, primarily on titanium dioxide. We do a lot of work in our group with bulk materials, but also trying to move into the nanoscale and seeing what type of effects the nanoscale size changes versus the bulk can have into a system. So things such as solar panels, photovoltaics, but also optoelectronics. So how are all these electronic processes that are available following some type of photoexcitation occurring within a material, and what type of relative rates do they have with one another? So kind of the first thing that I want to talk about is why is it that we might need non-adiabatic dynamics? Well, when we consider any type of initial calculation on solving an electronic structure for a system, the bigger, the harder it is to solve. I mean, if you try to solve it exactly, you're going to run into issues once you get past hydrogen. And so we work in density functional theory in trying to take a set of parameters and work with them in such a way that we can come to some type of feasible result that resembles what we might find experimentally. Now, I'm sure most of you are familiar with the Born-Oppenheimer approximation, and being able to split the electrons and nuclei separately allows for more of an easier stepwise calculation in solving these types of electronic structures. But when that happens, well, I should say, what happens when we move past that? What happens when the nuclear motion itself has a direct effect onto the electronic structure of the system? Well, this is the direction that we're heading, and the work that we're trying to solve. And so, like I mentioned earlier in the last point here, the relationship between the nuclei and the effects it can have on the processes involved in photoexcitation. So on the screen here are 2 different diagrams. The first one is just showing more or less a basic Jablonski diagram of you have some type of initial excitation, some photon hits the system and generates an electron volt. Well, what is it that this new charge carrier can do? You can have non-radiative relaxation facilitated by the chemical motion. You could have some type of fluorescence that is direct transfer back to the valence band with the emission of a photon. But you could also have intersystem crossing, spin flipping, and then phosphorescence as well. Now, with the figure on the right, this is a little bit more in relation to one of the projects that we've done with Dr. Krajewski, and looking at, you have this excited photon, and depending on how much energy is in the system, you can have some of the methods of relaxation that I mentioned earlier, but you can also have potential for multi-X time generation. And so taking this type of relaxed energy and producing multiple charge carriers, which when considering the applications in photovoltaics and charge collection efficiency, 2 for 1 is always better. And so the other portion of this that was mentioned in the title was nanostructured semiconductors. And so what type of effect can we have in spatially containing these molecules in different dimensions. And so when we're talking about quantum dots, we have spatial confinement in 3 dimensions, and just the general trend of reducing dimensions in which material can grow increases the band gap, as shown in this figure on the right. And so when you have this introduced confinement and its effect on the total electronic structure of the material, you can start to introduce prioritizing which relaxation mechanism might be preferred following the photoexcitation. And so ideally with titanium dioxide, one of the big things was people could use it to try and split water. And so another beneficial part of looking at small nanocrystals and quantum dots is the spatial localization, the ability to keep charge more toward the surface, which would be the reactive site, and allowing water to come interact with one of the charge carriers if the charge lifetime allows for it. So a little bit on methodology that we use. So I mentioned initially within the Born-Oppenheimer approximation, the ability to calculate ground state energies within density functional theory. That's a great starting point, but that doesn't always tell us the whole story as given the whole thought. So going from a ground state, we run it through a heating cycle, and then run molecular dynamics. And from that, we go into the nonadiabatic coupling between wave functions, and then also look at the rates of non-radiative relaxation, or the transition probabilities, given some initial electronic conditions. And so the majority of the calculations that we've run are done in VASP software. And so the conditions, the functionals that we use, generally is the PDE, which is period of P functional, and using fixed augmented waves, pseudopotentials, but we also work in a planar basis set. And so I guess the video is not going to run. So within these ground state calculations, we're trying to get a type of energy minimization by solving for a total structure, minimally moving the nuclei positions and resolving in this iterative effect until we get to some energy that meets the threshold. And once we have this energy minimization threshold, we can look at the converged wave function, and we can garner 3 different types of results. We can look at the total energy of the system, and in the basis of Kilin orbitals, we can find the orbitals and the electron density. We can also get individual Kilin orbital energies themselves, which will prove to be very useful in the following slides. So initially, just from this electronic ground state structure, that's something that's really easy to look at, just to visually comprehend, is the density of states. And so when we look at a total wave function and the distribution of available energies for each one of the electronic states, we can put them together in something like this. And so on the left-hand side, you can see that it's filled in red. So those would be populated states corresponding to the valence band, and then the unpopulated states in the right in relation to the conduction band. And so from this, we're able to generate one of the main observables that's easily matched with, compared with experimental results in absorbance spectrum. So the very top equation is the transition dipole moment, which is just looking at the spatial overlap of the electron density between 2 specified states. And so this is done in an independent orbital approximation within our methodology, whereas if you compare it to something like TDDFT, there's a superposition of transitions available for some type of specified excitation energy. So we can use the transition dipole moment in terms of to use this to generate the oscillator strength value. And so this Fij oscillator strength allows us to apply weight to some type of specified transition shown here, correlating it to some absorption coefficient. And so this can give amplitude for the absorbance based on the excitation energy. So once we can pull that information out, we want to start moving towards where we can try to understand what the nuclei moving may do to the total spectrum electronic structure of the system. And so in order to do that, most people don't study things at 0 Kelvin, and so we need to give it some type of ambient conditions, right? And we can put it into a heating calculation in order to give energies and velocities to each of the nuclei in order to simulate a correct temperature that an experimentalist might use in their setup. And so the velocities we scale at systematic time step until we get to more of an equilibrium and thermalization of the overall system. And so once we reach something we're happy with and the stability is good, we can take those velocities from the calculated step and we can put those in as initial velocities for molecular dynamic simulation. And so the molecular dynamic simulation takes those velocities and then allow for the trajectories to be calculated. And so, yes.
I'm not sure if I got the process behind that. So you actually do, so now you currently the ground state energies for a certain configuration, how you put on the velocities of these. What you end up getting then, so you get the second state, or what do you get?
So with the ground state optimization, we're just trying to find what would be the most optimal configuration of the nuclear. Once we have that, we know that it comes out frozen in the system. And so we just want to give the nuclei motion that would correspond to some ambient temperature and allow them to move in the way that we need.
So does that change the electronic structure then?
So yes. So that, and I'll get to that in the next slide and kind of show how that goes. So yeah, so we take those velocities that are calculated, put them into the dynamics, and then going from the dynamics, I guess with your question I'll start with. So this is a molecular dynamic trajectory of 350 microseconds. And each one of the colored lines vertically corresponds to one Kortshagen orbital energy. And so if we would chop this up into 1 femtosecond sections, each one of those sets of energy, vertical sets of energies, are calculated at each new position along the molecular dynamic trajectory. So you can see that energy is going to stay constant, and meanwhile, the nuclear position is changing and the recalculation of these energies.
So are the forces on the nuclei then calculated from these adiabatic electronic configurations?
Yes, yeah. So it's an adiabatic calculation. And so the point of running these calculations is doing thousands of ground state geometry calculations or energy optimization calculations along this trajectory is in order to, is to use the top three equations, which symbolize the same thing, this non-adiabatic coupling thing. And so what we want to do is we want to take a look at how orbitals at time step 1 and time step 2 overlap and how they correspond to one another in trying to get to a transition probability. So if you consider each of these great planes as a single ground state calculation with this comparison of the two, you produce a coupling. And so you build matrices with overlap between each orbital possible for transition within a system. And so, as I was saying, so if you just consider one small section of this as being one calculation and another, looking at overlap between wave functions of 2 times the velocity of coupling value to be calculated. And so we do that all the way across the trajectory. And what we're able to do is then look at the coupling values, take the average value of the couplings, and apply it to some initial condition. And so, in order to try and tie the nuclear motion with the electronic structure, we take these nonadiabatic coupling values that we've gotten, perform an autocorrelation function, and then take the Fourier transform, and the Fourier transform provides components to a red field tensor, which are the transition probabilities. And so, taking this red field tensor and looking at how time-dependent density matrix will change with just the dissipated portion of the dynamics can be put into this equation motion, electronic freedom, with the movable portion, the red field portion, leading to eigenvalue problem. And so, going from there, you can apply these operators to superoperators and get out eigenvectors and eigenvalues, which we can then propagate through some given time and solve for expansion coefficients. And so we could set some initial condition at a time 0, say we want to set from some band in the valence band to another state, the conduction band. We'll move electronic population and then allow the calculated transition probabilities to propagate to conduction time.
So you essentially dissipated components? What are those?
So the dissipated portion is the electron phonon portion. So how are the energies and wave functions changing with the nuclear motion?
So you have the corresponding to the dissipated fluctuated part? But you have both dissipated and fluctuated then?
That?
Normally you have dissipated fluctuations here and related fluctuations to dissipations.
So, I mean, can you find the difference?
Well, dissipated bits are dissipated with lose energy, and fluctuated bits are dissipated with gain energy, right? Apparently random motion, right? And so when you take the motion such that you get an effective dissipated part, if you look at the microscopically, typically you have a corresponding fluctuating part in the phase of motion that would, on average, cancel out the dissipated part so that it would still, for instance, in your case, you have a higher temperature. So if the only dissipated part you would have cooled it down because all the energy would be lost, but now you have a fluctuating district there, which would then keep you at constant temperatures.
I don't have a good answer for you right now. I'm sure Dr. Jon has a good answer for you.
What locations in the state are there? But if one is very far from the region, the station is 200 kilometers north.
But you're not, at this point, you can say anything about being found.
In terms
For
of
the initial conditions.
so the initial conditions that go back one slide. Oh. Yeah. So it's all in the beginning, some initial conditions. So say A and B. So you're taking everything away from the electronic ground state and you're pulling the electron out of the valence band and populating it somewhere up in the conduction band.
Okay. So you're throwing down the different states. Okay.
And so then, once we have these transition probabilities in between the states, we can apply them in two different methods. One being non-radiative relaxation dynamics, which is just energy put into thermal motion, but then also in time-dependent photoluminescence, and looking at what does the radiative emission look like, or could we get anything out of that? So when we are considering all of these possible transitions between individual electronic states, the emission can be calculated something similar to the absorption values in the ground state, but in terms of where the population is located in a given state at a given time. And so doing a summation over all possible transitions with some weight of strength can give this type of full integrated emission, where you see huge peak here close to 0 rate of vibration, which doesn't necessarily occur, but because we're looking at all possible sets of transitions, it's just an artifact of calculation. Being that the transitions are there, it just might not be realistic for the given system. And so on the other side of that, if we want to get out the non-radiative rates of relaxation, again, we set some initial electron configuration, and then the expectation values can be found for both the electron and hole, which are considered equivalent to these calculations. And then, assuming a single exponential fit, we can get a rate for the dissipation. Okay. And if there's no other questions on methods, then we'll jump into the silicon nanocrystals. Okay, so this was a project that we did in collaboration with Dr. Hobbie and Sam Brown, who are both here at NDSU. And so they were seeing effects of photoluminescence increase with the cooling temperature of these isolated nanocrystals. And so we wanted to take a look at what probable, or is there anything probable that we can see from either looking at dynamics modeling or adiabatic transitions that might correspond or give reason to the results that we were seeing. And so we looked at three different size silicon nanocrystals ranging 1 to 2 nanometers. And one thing to note is the surface capping with hydrogens, which doesn't necessarily portray the system and the ligands that they had on their nanocrystals, but in hopes of when we can find qualitative results, we reduce the amount of nucleon simulation to save time and computational resources. So one thing to look at, or to take note of when we're looking at these different silicon nanocrystals and what might differ between them is the coordination and the percentage of silicon atoms that have different coordination around them. So there are 3 different silicon atoms circled here in green, red, and blue, and they correspond to the number of other silicon atoms that are coordinated around them. So the green one has 4 silica, the red has 3 with 1 hydrogen, the blue is 2 of both silicon and hydrogen. And so looking at the relative percentages of surface atoms and which type of coordinations can give us a little bit of an idea of what we might see in terms of how might the dynamics of individual atoms vary given same set conditions. And so one of the things that we did was, this is taking a step back from the time integrated photoluminescence, but this is emission calculated along the electrodynamic trajectory just by taking the luminescence from the HOMO to the LUMO. So if we're looking at quantum dots or semiconductors that don't have any type of dispersion, we can assume that Cauchy's rule is going to apply, and the strongest emission is going to be across the area. And so in doing this, we can go at each set of energies taken at the oscillator string and the corresponding absorption value for that single transition, and try to pair that with the different size nanocrystals. Now the main difference between these 2 plots is we're looking at a low temperature and a high temperature system. And so you can see that the fluctuations in energy of individual chemical orbitals is reduced to the left-hand side, which is at 77 Kelvin versus 300 Kelvin on the right. And so this is just a little bit more in-depth look at what all 3 different size systems and the fluctuations look like. And so it's the same trend. The other thing to note is in agreement with confinement effects, the bigger we got, the bigger got reduced. And so we at least knew we were on track on that point. And so
work as an independent electrical evaluation. So how do you do it?
The system.
Or what are you neglecting? What are you neglecting here when you work in the independent electrical evaluation?
Well, I mean, given one excitation energy and collecting any other pairs of orbital that may contribute to the same excitation. I mean, it's solely just two-way functions and looking at the overlap.
So what are you neglecting?
Doesn't take into account for the erosion core production.
Oh, yeah. So there's no electron interaction in this sense.
How strong are you?
How strong is the reaction in this system? That I don't know. We didn't calculate the interaction, so I don't know.
Well, but when you neglect something, it's a good idea to see it.
Well, so one of the reasons that we don't have situations that we can count and quantify this. The other is the results that we got qualitatively match what the experiment was found. And so here, this plot here, so in solid is the low temperature, where the dotted is high temperature. And so we're definitely seeing photoluminescence increase with reduction of temperature, which is what they had measured and what we were asking about. So in terms of matching what they saw, the inbuilt approximation worked in this case. Now, qualitatively, we can have another discussion on that. But so what did we pull from this? One of the things that we did was, if you can see the difference between the bottom two nanocrystals and the top two. So the bottom is the low temperature 17 Kelvin, and the top two are at room temperature 300 Kelvin. And so here you can see that it looks more or less like one crystal. There's not much going into the lines, whereas the top two, you can see that it's kind of cloudy. And other people have told me they look like broccoli plots. And so the difference between the two is it's complete overlaying every atomic position along the linear trajectory. So with increasing temperature, you're getting these motions of the ions, and they're moving around quite a bit more. And so in correspondence to the different silicon atoms and the different types of formation that they have, the more coordination you have on the surface to some ligand, the hydrogen, or some other organic piece, the fluctuation is going to increase. And so, in this sense, we're very happy with the qualitative trends that we found. Now, the plot with the black boxes and empty boxes is a comparison of the intensity of low and high temperatures. And the filled ones are computational results, whereas the empty boxes up top were the experimental results. And so you can see the fit of the relative intensities versus the diameter of the nanocrystals matches with what they had found.
So, the smallest nanocrystals in the experiment is about 3 nanometers, right? How do you compare with what you have in the little bit different using
Right. Well, I mean, when we're looking at something our order of 2 nanometers in diameter, I mean, we're starting to get to limits of what's computationally feasible.
Yes.
Okay. And so if we can get some type of relative size distribution that can match what they can isolate out in terms of fine selectivity for nanocrystal radius, you can try to compare in that sense.
So you reduce the prayer.
So, just to clarify, so I mean, you didn't see like you haven't found certain degree.
No, we did.
point out with the diagram is using above symbols here and show us where is your 220, where your models and where is the experiment.
Well, so I mean, the 220 is going to be here versus the bottom of the experiment is here. So,
And you have a comment about slopes.
well, I mean, so the trending line fit the data points, which is like the qualitative aspect was matching qualities. And so, from this, basically, what we pulled away was we believe that the surface passivation for these nanocrystals and the relative dependence on temperature allows for this increased photoluminescence at lower temperatures versus the higher temperature regime of the silicon nanocrystals. And so the next,
Before you finish that, do you have a physical reason why the lower temperature would give you higher temperature?
so when considering the two energy fluctuation plots, when you have low temperature, the fluctuation is minimal in the function orbital energies compared to high temperature. This is here. So when we look at calculating the oscillation rate, which is dependent on emission vacuum moment, as you change the nuclear positions, you can decrease the overlap between a set of given orbitals, and so that you would reduce the amount of absorption or reverse emission between those two states. And so by changing the nuclear positions, you can have a reduced intensity of emission.
Well, there's not a random argument. You could also increase it, right? You might also increase the overlap.
Right, right. But that's not what we saw in the calculation. We saw that it increased the emission.
So the Baltic area is very specific to that very specific structure.
I mean, well, I mean, in this case, yes, that is what happened. I mean, I guess I don't know. I would have to look at some of the other nanocrystals themselves, and therefore exactly.
So you would not be surprised if a different nanocrystal would have exactly the opposite effect.
Yeah, I mean, it depends on if you could have some type of stabilizing ligand on the surface, and if, depending on the matrix that they put it in, you could get some function of motion on the interaction between them.
From point of view of intercepting of energies of different orbitals is what is the
So, one of the other things that can happen in these types of calculations is, so the line stays consistent, the color stays consistent, sequence all the way across. But what you can actually have is, even though the state energies seem like a solid line, you can have orbital distance switching, and so you can actually have different orbitals populating, say, this top line, because this is just kind of a ground state trajectory, whereas if you were actually in like a kind of excited state, you would be repopulating these electronic states.
So what are the conditions for this?
Well, so then I mean, if the indices are switching and you not realize it, then you can have different density localizations of the electrons, and those can change the emission properties.
is it sufficient? I can take a conclusion.
Yeah, but
Most of us level strength is stored in the color information, which are specific shapes of orbit and specific order of orbit. They are modular. But as molecular dynamics is launch, one because you may penetrate, because you can see you may penetrate deeper into conduction tank. There was a coma, you penetrate deeper into burn tank. And they would contribute emission, but they do not pop you away because of pressure, because of the excitation. We always relax the coma. And this molecular modeling will drive optical effective programs away from being the lowest position. Thus, there will be no emission. Is that what you want to say?
That's a good way to put it. Okay.
So, one subject is emission from the common lumber. Silicon, bulk silicon, we have less gap semiconductor. So, new applications in the larger working tools, in the crossover with the NDSU, and then the try to experiment. Where does it occur? Does it release from the
So with the Kornbach systems themselves, I mean, we're just speculating solely at the gamma point. I mean, if you want to move into something that's in between, and you're trying to look at indirect transitions, like phonon system transitions, or it would have to be an initial calculation of moving the K point, adding some additional momentum depending on the dimensionality of the structure, and trying to do single point calculations at that point and see what the structure is like.
Yes, it's just that you are reproducing trends seen in 3, 4, and 5 nanometer corridors where they are individually indirect engineering. But you are working in only taking transition between homo and human. So, what are your thoughts?
What the question was presuming.
The cumulative.
How do you define a vector in quantity?
Oh, you don't need to. Even if you work in double point approximation, you will see that the lowest with the homo condition is going dark all the time. That's how with indirectness calculation. Even if you don't label it specifically with the vector data.
Diameter is affected by the set. What is your quantitative measure of its condition?
Quantitative measure is the animal. Also, what is strength?
How do you define for each diameter of this condition?
Well, I can only do two, but that's a school is about 3 nanometers.
Any fundamental reasons for this?
Fundamental, well,
Or it is just expectations?
I that's a school. But I know for sure that the bigger you make it, the surface effect that you observe is very important. It's just bulk. Right? It is bulk of the low school that conditions the system.
Soon nanometers is very hard to calculate.
Again, what?
Soon nanometers is get really smaller than that.
So what you're saying is the experiment is still only
So that's to tell everybody else, every project, I don't know how often I will briefly say about direct, indirect, and how the service changes that.
So, I mean, looking at direct versus indirect, either absorption or emission, regardless, there has to be some momentum change that has to account for the phonon-assisted type of transition, or some additional velocity or thermal motion added to some type of surface
understood this proposition, that bulk silicon has an indirect transition. That would mean that the bottom of the valence band and the top of the conduction band are at the same wavelength, right? Whereas from what I've gathered from the discussion, at the boundary bits actually that they do coincide, right? So they direct transition. That's what you're saying. Okay.
Okay. So, okay. I will try to hustle a little bit. Okay, so the next set of systems is plastic tightening clusters. So they're small groupings of oxygen metals used in pollutant reduction, also as electrodes, in different types of cells. And so one of the things that we want to look at here is, one, how does the size of the cluster affect the electron structure? Does it match our expectations? And knowing that the titanium dioxide is not a good light absorber, absorbing UV, what does the addition of some type of organic ligand do to enhance the visible region absorption? And can you get some type of charge transfer event that can promote reactivity on the surface of the cluster? So just to briefly show you one model, I guess I have two models. So the first one is, this has 6 titanium atoms in it. And looking at the density state distribution, you can see that the electron population in terms of where the band gap lies is dependent on the set of ligands that is attached to the surface of the metal cluster. So as propanol, you see a fairly clean band gap, whereas here you have populated states, well, new introduced in the populated states, here in conduction band, driving almost a non-zero band gap in the system. So when looking at just the partial charge density of the ground state, you can see that the hormone is localized not on titanium atoms themselves, but as soon as you get to the conduction band, you're looking at the centrifugal on the titanium atoms. And so this are the energy fluctuations again, and then this is the dynamic emission. So emitting here close to the relative band gap energy. And so if we would look at, well, I guess this is going to be the first look at figures that show charge carrier density and how it changes as a function of time and space. And so in these figures, green is the electron equilibrium, so there's no change in the population. Whereas on the left side, we have some initial photoexcitation, and so we're taking loss of charge, is shown as blue, gain of charge is shown as red. So you're generating a whole and populating an electron up into the production band, and following the dynamics calculated through dynamic couplings, you can see the relaxation of the charge carrier and how it distributes its energy as a function of time. And so the values of UFDI are just the transition energy to the initial excitation energy getting to the system. And so for this, I mean, they're all close to 40 even, so we get here to about 7.8. And the transitions, since they're weighted by the oscillator strength, can be ranked according to their oscillator strength and showing the most probable being the highest oscillator strength value. And so these rates, given as a logarithmic scale on the x-axis, so you would fit the time scale for the electron relaxation here, that would be close to 10 picoseconds. And whereas this type of excitation occurs from, say, the homovocal, which know what the electron relax to, and so it can stay constant energy. Whereas if you look at charge carriers generated deeper and higher into the conduction band, you can see that the charge carriers are populating different states as a function of time. And so the main comparison for this is looking at this larger system, 17 titanium atoms. So with this isolated, no limits attached, the density states provides a spectra looking like this, the band gap is close to 2.8. But when you add methanol and acetic acid to the surface, you introduce this new electronic state that is now populated So you increase energy between possible states here in the valence band, but you also close the band gap energy with the conduction band. And then another set of organic pieces with propanol and acetic acid does not show the same trend in population of new states. And so the specific ligands that you put on the SIPs can directly affect what transitions are available to the system. And so this should say TI-17, not TI-6. So instead of looking at something that's just localized around the surface of the core and the oxygen, you see something that's localized closer to one of the living groups on the surface of the cluster. And then going back to conduction, then you see it then localized around the titanium atoms. And so why is that good? Well, if we're looking for some type of living to metal charge transfer event, that's going to show up with this reduced absorption value and provide absorption in the visible region. Now, one of the things that you can look at in terms of this is, so instead of having more or less compact function orbital fluctuation values, we now have this very squiggly piece that corresponds to the rhythm that was attributing the light tendency to the hormone. And so what actually happened during this dynamic simulation was this ligand broke off the surface dissociated. And so as a function of time, this orbital energy value finally found a settling place that was off of the surface of the system. And so the absorption region comes in here between 5 and 700, and then looking at the emission over the set over the course of the dynamic trajectory is here at about 1,000, which is close to band gap energy, but then this long tail of what going from time and off as this fluctuates. And so the dynamics for this system, you have excitation energies lower than what we saw for the previous model. But what we also have here is when we look at this relaxation time close to a picosecond for the electron, and the whole relaxes here close to a nanosecond. It's a very large charge separation lifetime, which allows for reactivity of the system with something such as water as a photocatalyst. And so, yes.
So, when you show the structure that has the evidence, kind of a whole combination, that's something I haven't seen.
So, back to Dr. Besky's question about anything we might be missing in terms of electron-hole interaction. In this case, there's still not taken into consideration, but what you can calculate is you can calculate radiative decontamination, non-radiative decontamination, and you can look at the time scale to which that might occur, say for the Einstein coefficients, and you compare that to what the non-radiative relaxation rates might be. And so you get an idea of, well, are we on the right time scale and the water pressure and the ignore decontamination rates? Okay. Well, okay. So I guess, so I have some of the work that I've been doing over the last couple of summers is not conclusions. So in concluding with product type mix, so we did see a change in what energy states are available in the electronic populations given the size of the cluster and the set of organic ligands on the surface, and then how that corresponds to living metal charge transfer hypothesis, and can we direct experimentalists to use this type of system with these parameters in order to produce the best photocatalyst. Okay. So I've been working with Perovskite materials for the last couple of summers because they are very good material, photoactive material for photovoltaics. They're also very cheap. They're easy to make, and efficiencies have been climbing. So I showed you the big MREL chart of photovoltaics. you see that the rate of efficiency increase is very rapid. But these types of materials have inorganic and organic portions with lead iodide lattice framework, and then methyl ammonium cations that are freely rotating inside the material. And so some of the questions surrounding that have been what's driving these really high efficiency values for materials, and can correlate that to any type of specific molecular motion. This is a video of Dr. Kilin and I. Maybe it's not going to play. Well, if it did play, these ITOs glasses are covered with titanium dioxide, put into the oven for a little bit, cooked, and then you drop methyl ammonium and lead iodide solutions onto them, and then they anneal into this perovskite material. And so one of the simulations that we wanted to do was we were looking at this bulk material. So we're building a supercell of this perovskite material as a 2x2x2 of cubic unit cells. What we're able to do is try to model a larger portion of this material. And so one of the things that you haven't seen yet, so this is plotting of correlation of the Nonadiabatic couplings, which I had described earlier. But then this plot also resembles the reticle tensor itself. And so the transition probabilities in between two specified states is represented vertically. But since you see the main probabilities on the diagonal, meaning that states of DC energy are more probable to have transition. And then this is just another way to plot the rate of transition energy versus the log of the rate trying to do some to extrapolate out some higher forms of energy. You want me to keep going? Okay. So looking at both materials themselves, we were able to get utilization rates for electrons close to 2 picoseconds with the whole corresponding to something a little bit quicker. And experimentally, Vogel and workover found utilization in materials on the order of 4 to 800 femtoseconds. So we're in the right ballpark. So here is, in terms of populations as a function of time, the relative difference between the energies of the populated states and possible excitation energies that could be produced, where once the electron hole penetrates to the homo-lumo, you get back to a constant value which corresponds to the band gap energies, the integrated emission of the possible energy difference between the charge carriers. And so, one of the other things that we've done is we worked on a quantum dot model of the perovskite material. So instead of doing a supercell, we took 3 unit cells and we put them together into a quantum dot of the material. And so looking at the ground state energy structure material, we were looking and finding that the majority of the charges still localized on iodine, but once you switch to the conduction state of the lead, which is what is experimentally seen expected for these materials. And so now the video is going to work. So what you would see is the density state is a function of time plotted a number of steps in the trajectory. You would see this dynamic energy band fluctuating back and forth, which would correspond to relative energy fluctuations found here in the Vogel energies. And also, you can see how the absorption spectrum will shift in and out with the molecular motion. And then both of those for the low and high temperature region. As the cubic phase is often found at high temperatures above 320, it's interesting to see what the temperature effects can be on these systems. And so One of the other things to look at is what ion radial distribution function as it propagates down the trajectory. And so here are three different sections of trajectory sampled and plotted on top of each other, just for lead iodide to show you that as it propagates along the trajectory, potentially in an unnatural temperature or just phase, you start to see phase shifting based on the inorganic lattice bonds of the system. And so one of the other things is going through the Einstein coefficients, you can calculate radiated lifetimes. And so for the lunar HOMO, the transition would be about 102 picoseconds. And so when we're considering all these different relaxation mechanisms, how to compete with one another, knowing relative timescales is a good way to order which mechanism may be most probable. And so calculating radiated lifetimes and then looking at where the excitation might happen, one of the things about quantum dots is that they can experience much less time generation. And so one of the reasons we looked at this integrated emission is to start looking at where can we find emission above the band gap energy and could correspond to anything that would promote this type of process. And so the quantum yields between the radiated portions and the non-radiative relaxations for the high temperature gave 97% quantum yield versus 4% for the lower, which both correspond to what's been experimentally measured. So one of the things that Dan and Dr. Grisky have done is they've been working with calculating time generation rates in the quantum dot system with respect to the excitation energy and how it relates to band gap energy itself. And so the single to lifetime generation is shown in green with increasing rates as you increase above the band gap, factor above the band gap, whereas the opposite more or less stays the same. Obviously, we have a discussion on this now, but for interest of time, so with the transition probability, then you see them primarily along the diagonal, and the majority of the probabilities in this instance are occurring in the valence band. So transitions will occur faster in the pole, which is what is experimentally measured for these systems. And so if we look at one of these types of transitions, it's the same transition that I showed earlier. You get the initial population electron and relaxing after layers of 16 and 17 picoseconds at the low temperature, and it's with increased temperature, which is what we'd expect. And so, ideally, if we follow gap law, the larger the energy amount that needs to be dissipated, the longer it's going to take. And so that trend follows for these higher energy transitions. Once we get down to the lift regime, we can start looking at symmetries of orbitals and how they overlap with the system itself, and also with generally slowing the rate of non-radiative relaxation. And so the rates themselves are calculated in a range anywhere from 5 picoseconds all the way up to 20, whereas at the higher temperature, you can see that they're all single digits, following the trend of increased temperature on rates of non-radiative relaxation. I will skip this portion and just say, so nonadiabatic dynamics is necessary when looking at systems that are in motion and how nuclear components can implicate or change the electronic structure leading to different charge carrier efficiencies and materials. And so thank you to these people that come up and Dr. Grisky, Dr. Hobbie, Sam, and then I'm going to stop, and I will have to answer more questions.
So it's not if you had that out, if you had out. If your friend asked for another
So when I use the term electrotrajectory, so there's different ways you can think about it. The way we do it is ground state trajectory. So how, say we focus on one atom, how does that atom move in space as a function of time? So if it, say it starts here, ends here, the trajectory, you could have something in this sense. Whereas if you start doing electronic, like excited state trajectories, where you would repopulate electronic structures and run dynamics again, then you could potentially have some fluctuation in just like a ground state dynamic trajectory. So how does the molecule move in space? Right.
So it's not kind of vibration
Yeah. So there's two different ways to do this. The way that we do it, so you can set the velocities from our heating and let the dynamics run. So we're forcing the atoms to move according to some ambient temperature. Well, that's all considered to be ground state. So the electronic structure doesn't change at all. If we would perturb the electronic structure and ask it to be in a different state, we're going to start shifting the forces in the system that could potentially move some of the nuclei in a different direction than what we see in the ground state. So there's just competing effects of where the electron density lies and how the energetics are going to try and bring it to some equilibrium.
So how do you count? So you get energies, right? You get force tolerance, but the forcing for your atom would be different in the excited state than ground state.
So you can manually populate excited states. So if you do the ground state structure, it builds. So you get out to your function orbital and where the electron density lies, and say you would populate one of those. So now you're following a different series, or directing that a different way. Because it's still trying to calculate the dynamic trajectory, but it's going to have a different set of energy potentially associated with it.
So when you do the energy forces, you actually calculate various energies, various directions, calculate gradients of those potential energies with the force. How do you get the energy forces?
Yes.
You actually do that with expensive.
Yes.
Yeah.
The potential energy surface can be computed once and forever, or can be computed on the fly only in the original space where we need them to compute the next set of forces. So what John is doing is just computing point at the potential unit surface and slope. And then as soon as we move time, we forget about it. We compute again.
So you get different forces depending on whether you're excited or not excited. So then you take that into account in your analysis.
I mean, it's taking excited state into account for initial doesn't happen because we're not populating anything.
It is not among the results that are getting presented, but it is possible other people are doing in the same way.
So what computers do you use?
So I mean, we run everything on the headphones computing cluster USB. I think they have like 700 some processors on it, but it's a computing cluster that they have set up for it.
How long would one of those trajectories how long I think it can take?
So depending between the different, one would obviously depend on size and the accuracy of calculation, but it also is dependent on the material under study. So the prototype materials we found actually take a long time to analyze, and so the heating process takes much longer. Versus say the silicon and titanium, which that to run an energy trajectory might take a couple of days.
we monopolize the cluster for a while.
Yeah, they can. I mean, there's some people in our group that do mock or superconducting research whereas I know some of the companies are the most expensive because you're taking ground state overlap and some calculations inside one type of calculation. But there's one.
But you're not doing any development of the algorithm, that's all done.
Well, no, so the heating method is too fast. Everything after that is something either that's done or coworkers have written. So we play around with that some in trying to do that.